Okay, so this is a simple example like the ones we spoke about in class the other day, where we've got a block resting on top of a table, and there's a spring scale that's applying a force of tension upwards, taking some of the weight of the block. So our job is to calculate the size of the force normal when the force tension being applied is 35 newtons, and of course that is being applied upwards from above. So we start off with defining our frame of reference. We just make sure that we're saying everything that points up is going to be positive and everything that points down, let's say, is negative. Then we'll work with our free body diagram. So again, I just simplify this. I draw a box that represents the block, and then I put the force arrows coming out of the block. So the weight arrow is pointing vertically downwards. It doesn't really look it in the picture, but it is supposed to be anyway. And that's the weight, which is also mg, mass times gravitational field strength. I'm going to have two forces pulling up. So I'm going to have the force normal. Now remember, the force normal is a contact force, and it comes about from the surface of the table. So when sometimes we can overlook this, but the force normal is being applied at this point right here. Okay, it's being applied at the contact point from the base of the block. So that's why sometimes in free body diagrams you'll see the force normal starting down here. Now in a free body diagram, it doesn't make too much of a difference. You can also put it starting from here or put it up here somewhere. It doesn't make too much difference. But just so as you know, the force normal does come from the surface of the table, and by right should be coming from the bottom of the block. The force tension, of course, is being applied at the top of the block, so I've just added that in there. So now what we do is we apply the technique. Here's the logic, okay? And I'll say this in words. You sum the forces, summation symbol, forces in the y direction, and you basically just add them up. So you have a quick look. What have we got? Well, we've got a force tension pointing up. I've got the force normal pointing up. Those ones are both positive by my frame of reference. Then I've got the weight. The weight is pointing downwards, or the force of gravity is pointing downwards. And the whole thing, of course, because that's down, that's negative by our frame of reference. The whole thing by Newton's second law is equal to the mass of the block times its acceleration. Now here's the logic bit. You say to yourself, well, is it moving? Number one. It's not moving, so therefore the acceleration must be zero. Okay? So then the right-hand side of that term goes to zero because the acceleration is zero. So you're saying the force of tension plus the force normal minus the weight is all equal to zero. Therefore, the force of tension plus the force normal is equal in magnitude to the force of gravity or the weight. Rearranging then for the force normal, that gives us the force normal equal to the weight of the block minus the force of tension. Of course, that should make a little bit of sense because the table now only has to carry part of the block because the spring scales is carrying the rest of it. So it's at this stage now I can sub in the numbers. The weight is equal to its mass times gravitational field strength. So that's 10 kgs times 9.8 meters per second squared. Minus 35 newtons, which is the force of tension that's recorded in the spring scales. And that works out to be 63 newtons. So there you go, force normal is 63 newtons. So I guess the key point here is, key takeaway is, the force normal is not always equal to the weight, okay? You gotta look around and see what else is going on. It's only equal to the weight when it's lying flat and there's nothing else going on. No other forces being applied, okay?